Hi all, I am Giulia Baldazzi. Sorry. Yeah, I can take it. Yeah. Okay. I'm Giulia Baldazzi. I'm a biomedical engineering and a postdoc at the MediSP Lab, so Medical Device and Signal Processing Lab at the University of Cagliari. So today I'm going to present you part of the research work that I carried out during my PhD. So fetal ECG extraction from non-invasive multichannel recordings, and specifically the investigation of the non-local median and optimal shrinkage algorithms. And this research is carried out in collaboration with Professor Auti. So, non-invasive fetal electrocardiography is based on the acquisition of the fetal cardiac electrical activity as electrocardiogram, and it is performed by simply applying surface electrodes on the maternal abdomen, and it constitutes a promising tool since it could allow for a prenatal, low-cost and risk-free monitoring, but also thanks to its non-invasiveness, it could be also exploited for long-term applications. Furthermore, it could enable also the assessments of all pathological states inducing alterations in the fetal ECG waveform morphology, like some form of congenital heart diseases and fetal arrhythmias, but also could enable a prompt treatment in early pregnancy or immediately after birth. However, the non-invasive fetal ECG suffers from several critical issues that overall lead to low quality fetal ECG signals and thus preventing the adoption of this technique in the common clinical practice. So at first, the recorded signals are very weak and non-stationary because of the small size of the fetal heart, but also to its time-varying orientation and movement. Furthermore, different media are interposed between the source, so the fetal heart, and the measuring electrodes on the maternal abdomen, whose shape and electrical properties change during the whole gestational period and hamper the acquisition, also introducing distortions in the last gestational period. Furthermore, different instrumental noises, but also and mainly bioelectrical interferences are present, and the latter are mainly due to the mother and specifically to the maternal ECG, as we can see there, and but also to her respiration and the uterine contractions, and overall they overlap with the weaker fetal ECG both in the time and the frequency domain, and as such requiring very powerful signal processing methods for the fetal ECG to be recovered. So in the last decades, several signal processing techniques have been developed to recover high quality and reliable fetal ECG signals, but nowadays the identification of a clinically useful fetal ECG signal is a challenge. So typically the non-invasive fetal ECG recordings firstly undergo a pre-processing stage in order to mainly remove the noises which are out of the fetal ECG band. Then a fetal ECG extraction process is performed to retrieve the fetal ECG component, and these steps mainly aim at removing the maternal ECG component, and it constitutes the more challenging task. Then an additional post-processing stage may be needed in order to enhance the fetal ECG content and remove the residual background noise. So in the light of this, we focus on the development of a fetal ECG extraction algorithm. So today I'm going to present you a novel algorithm for the fetal ECG extraction, and specifically for the recovery of morphologically preserved fetal ECG signals, which were acquired from non-invasive abdominal recordings. So here is the main processing pipeline for the fetal ECG extraction. So at first, abdominal signals, according to our algorithm, are preprocessed, and then an accurate maternal heart peak detection is performed by considering all heart peak annotations that are in common between the two muscular channels. Then each maternal beat is segmented and denoised by the optimal shrinkage by assuming an a priori noise level as input, and then by the non-local median algorithm that here has been adapted for the multi-channel case, So for each maternal beta, median template is estimated by considering a fixed number of most similar neighbors in the manifold, and as such a noiseless maternal ECG is reconstructed by tapering each template and putting it into the corresponding temporal location. So as such, by subtracting these noiseless maternal ECG from the abdominal recordings, so pre-processed abdominal recordings, we can estimate a raw fetal ECG, and on this basis, we apply the denoising of the maternal ECG again by considering, in this case, a more robust estimate of the noise level for the optimal shrinkage, and then followed by the non-local median. So by subtracting this latter, the noise, the maternal ECG, from the pre-processed abdominal recordings, we can estimate a more accurate multi-channel fetal ECG signals. And on this, we performed a channel selection based on the coherence of different peak detectors. And then here we try to identify the fetal R peaks. So fetal R peaks are accurately detected by applying the singular value decompositions and then choosing the reconstructed SVD component showing the highest fetal content, on which we later perform the fetal R peak detections. So this latter selection was based on signal quality indexes that were provided in the reported scientific literature. So finally, the fetal ECG is enhanced by non-local median post-processing. So as such, we decided to evaluate the performance of our algorithm, so we tested on two available datasets. So a freely available real multi-channel dataset and a physiologically plausible synthetic dataset. And this latter was simulated by adding different non-stationary realistic noises with different amplitudes. And it was done in order to challenge the algorithm even more and test its performance also in those cases where typical blind source separation algorithm cannot perform accurately. So in the simulated cases, we obtained 4 different subsets of 10 pregnancies each with different signal-to-noise ratio. So the performance was quantitatively assessed in terms of fetal R peak detection of a state-of-the-art QRS detector, and in terms of morphology preservation, obviously in the latter case only on synthetic signals. So this latter analysis was evaluated in terms of Pearson's and Spearman's rank correlation coefficients and the root mean square error. So as regards the results on synthetic signals, we can see that the fetal R peaks were accurately detected in the fetal ECG signals extracted by our algorithm, even in very challenging cases, so in all examined subsets mainly, thus encouraging the use of this algorithm for a reliable fetal heart rate monitoring. Furthermore, by looking at the recovered traces, we can see that the fetal ECG signals were faithfully recovered from a morphological perspective, also in case of very low signal-to-noise ratio, which is very important in the perspective of its use in real scenarios. As regards real signals, the results showed that the algorithm offered very good performance in fetal air peak detections, showing median accuracy values of above 96% and true positive rate values, median true positive rate values of about 98.5%. By looking, however, also at the recovered trace in this case, the capability of our algorithm of performing a morphology preservation recovery is quite good. So in conclusion, here I presented a novel fetal ECG extraction algorithm showing promising results, not only in terms of fetal R peak detection, but also in terms of morphology preservation. And its performance revealed its ability to recover high quality and morphology preserved fetal ECG signals from non-invasive multi-channel abdominal recordings. thus enhancing its potential usefulness also in a very inconvenient context as real long-term applications. Furthermore, despite its promising results, and especially in the perspective of its adoption in a multi-channel non-invasive fetal ECG monitoring device, which, however, could allow for a more accurate fetal cardiac assessment, some study limitations should be mentioned, as the lack of a clinical validation of the recovered fetal ECG morphologies, but also the lack of a clinical assessment on unhealthy fetuses as those affected by fetal arrhythmias or other pathologies inducing fetal ECG morphology alterations. In conclusion, in this study I used 20 minutes long traces, but for those researchers that are interested in shorter data but accompanied with synchronized pulse width Doppler, our group recently released the NYMPHEA dataset with these characteristics. And all this research has been carried out under the PRIN ICT for MAM projects. So thank you all for your attention.
So thank you very much for this impressive presentation. Maybe I start with a very quick question. So sometimes algorithms are novel and good before knowing it, so it takes time to generate the data, to validate it, etc. But it's too late for filing a patent, for example. So my question is, have you considered to file a patent, or has a patent been filed for this method or for the algorithm?
Actually, at the moment, not, because we are still testing it. Here I perform a test only on a real data set, so we are looking for other results on other real data set, obviously. And furthermore, obviously, a comparison with other state-of-the-art scientific proposals, signal processing techniques is still needed, so we are working on it.
Okay. Any other questions, comments? Okay. First you.
Nice presentation.
I
I want only to know exactly in which condition do you collected those data, because they were very fine. The maternal and fetal ECG were very, visible on the recording and so on. And I know for sure that when you go into a clinic, it's not the same thing. It's a mess. So you can get signals that are very, very bad in terms of possibility of separation. So.
Actually here I used a freely available real data set that was acquired by the Matoni et al. Group. So they were at rest, and so and also not in the initial, in the first phase of the pregnancy. So maybe it's the reason why the maternal and the fetus were quite visible. And obviously we would like also to test it on our data set that is performed on early pregnancy, so it's more challenging in this sense. But we need longer traces, so in order to have the synchronized pulse with Doppler, we need to take them shorter. So it's the trade-off between them.
I would like to ask you, for getting the fetal ECG, did you always use the same electrogeometry and location, independently of the maternal gestational age, or did it change?
Yeah, actually they use the same electrode positioning for all the measures.
Okay, thank you.
Okay, so then I'd like to thank the speaker again.
Thank you.
Thank you.